$6.9 trillion. That is how much wealth the United States lost in a single year. Not in war, not in natural disaster, in a financial system that almost everyone believed was mathematically sound, and that no one saw collapsing. Well, almost no one. In 2000, a statistician at JPMorgan published a 12-page paper in a journal called the Journal of Fixed Income. The paper described a mathematical idea for modelling correlation between credit defaults. Buried within that paper was a single algorithm, a mathematical object Lee called a copula. It was designed to answer one simple question: if one bond defaults, what does it tell you about the next? To understand why, we must consider banks. In the early 2000s, banks looked at bonds very differently. When a bond defaults, it means the borrower can't pay back the money they promised, so the bank who lent the money may not get it back. Their mental model for the mortgage default risk was essentially this: each borrower is independent. If one defaults, it tells you nothing about the next. And if that is true, if defaults really are independent events, then bundling mortgages together is a straightforward risk reduction strategy. You are diversifying across unrelated outcomes. Mathematically, independent events satisfy clean factorization. The joint probability of two independent events, A and B, is simply the product of their individual probabilities. This is a reasonable model for a lot of things: radioactive decay, coin flips, genetic mutations. However, it's not a reasonable model for mortgage defaults, because mortgage defaults are not generated by individual physical processes. They are generated by economic conditions, and these economic conditions are shared. When a regional employer closes, unemployment rises locally. When unemployment rises, defaults rise. When defaults rise in one postcode, they tend to rise in neighbouring ones too. The defaults share common causes. In statistics, we say they are correlated. The correlation between two random variables, x and y, is defined as their covariance divided by the product of their standard deviations, a number bounded between -1 and 1. When standard deviation is 0, the variables are uncorrelated, knowing the value of 1 tells you nothing about the other. When standard deviation is 1, they move in perfect lockstep. The key thing about mortgage defaults is that this is not a fixed constant. It is a function of economic conditions. In calm times, it might sit around 0.2. In a nationwide recession, it moves towards 0.9 and towards 1. And the mathematics of what that does to a bundle of mortgages is devastating. The models assumed that standard deviation was fixed, stable, a property of mortgages themselves. It wasn't. It was a property of the world those mortgages existed in, and the world was about to change in ways that models could have never considered. There was a second problem sitting underneath the first, and in 2008, Goldman Sachs accidentally told the world what it was. The banks weren't just assuming independence, they were modelling the distribution of defaults using the Gaussian distribution, known commonly as the bell curve. Under the Gaussian, extreme events are exponentially rare. A 10 sigma event, 10 standard deviations from the normal, should happen roughly once every 10 to the power of 23 years. In August 2007, Goldman Sachs CFO, David Viner, told the Financial Times that they were seeing 25 sigma events several days in a row. That is not bad luck. A 25 sigma event under a Gaussian should not occur once in the entire history of our universe, let alone on consecutive trading days. What Viner was actually describing, without quite saying it, was the distribution was wrong. Real financial markets have fat tails. Extreme events are rare, but nowhere near as rare as the Gaussian predicts. The model wasn't slightly off, it was wrong in precisely the way that would cause maximum damage when everything went bad at once. So here's the strange part. A formula existed that could have captured all of this: the correlation, the fat tails, the linked fates of hundreds of thousands of mortgages. So what went wrong? To see where the error started, we should begin by looking at David Lee. David Lee was an actuary before he was a quant. Actuaries spend their lives on one problem: how do you mathematically model the way risk evolves over time? This included mortality tables, life insurance, joint life policies. That last one is where Lee's thinking started. There is a real statistical phenomenon, sometimes called the broken heart syndrome, where when one partner in a long marriage dies, the other often follows within months, not because of shared genetics, but because their lives were completely intertwined. Same routines, same social world, same reason to get out of bed in the morning. Their survival times were correlated. So the mathematical challenge was clear. How do you model the correlation between two variables, two lifespans, two bonds, two mortgage pools, without forcing any particular shape onto either individual distribution? Lee's answer was a copula. So what actually is a copula? A copula is a function that links two separate probability distributions into one joint distribution while leaving each individual distribution completely intact. All the copula shows is the correlation structure, nothing else. The individual shapes stay exactly as they are. This is guaranteed by a mathematical result from 1959 called Scalar's theorem. What this guarantees is that C is modular. You can plug in any marginal distributions you like, and the copula handles how they are linked. This is what made Lee's approach so powerful. You no longer need to assume both bonds follow the same distribution. You just needed a way to describe how their fates were connected. But what was Lee's approach? Lee's specific construction used the Gaussian, the bell curve, as its foundation. The formula is this. U and V are simply each bond's default probability. How likely is this bond to fail? They are numbers between 0 and 1. The formula takes those two probabilities and uses ρ, the standard deviation, to describe exactly how their fates are connected. This is the geometric interpretation. At 0, the two bonds are independent. The surface is symmetric in every direction. At 0.95, it has collapsed into a ridge along the diagonal. Both bonds are now almost the same bet. If one defaults, the other is almost certainly going to as well. For the first time in financial history, you could take two bonds with completely different risk profiles, different markets, different everything, and mathematically describe how their fates were intertwined. You could price correlation itself. Wall Street had never been able to do this before. Traders called it the formula that conquered risk, and they were right for about 4 years. The thing that broke the economy wasn't the formula at all, it was a single number, the standard deviation, and where that standard deviation comes from. To estimate Lee's copula, you have to input ρ, the correlation between defaults. The banks estimated it using historic data. They looked at how correlated mortgage defaults had actually been over the previous 10 years, computed the number, and used it going forward. The 10 years they were looking at were 1995 to 2005, one of the longest, most stable housing booms in American history. Defaults were rare, regional correlations were low. ρ came out around 0.2, and that number was stamped into every model, every CDO, every rating, as if it were the fixed property of mortgage markets, rather than a measurement taken during an unusually calm decade. A correlation estimated from a boom is not the universal truth. It is a snapshot of one specific, historically unusual period. Feed the same calculation data from a recession and ρ comes out near 0.9. The banks weren't measuring the true correlation between mortgages. They were measuring the correlation between mortgages during a period when almost nothing went wrong. By 2008, the gap between those two lines was the global financial system. Every CDO priced using a ρ of 0.2 in a world where the true ρ had become 0.9. This was a catastrophic misprice. Not off by a few percent, off by the difference between a safe, diversified portfolio and a single concentrated bet that everything fails at once. Lee wasn't blind to this. Lee's original 1999 paper noted that the correlation is not stable across economic regimes. The model's outputs are sensitive to the assumed value of ρ, and that ρ should not be treated as fixed. The warning was in the document. What the industry did was take the formula, remove the caveats, anchor ρ to a boom era data, and deploy it at a scale to justify trillions of dollars of products that they believed were safe. The formula didn't fail Wall Street. Wall Street decided what the formula said and what they wanted it to say, and stopped asking whenever that was true. That distinction between a model being wrong and a model being misused matters, because the same distinction applies to what is happening right now. The crisis exposed 3 simultaneous failures in the Gaussian Copula. ρ was not stable, the tails were not thin, the Goldman 25 sigma events proved that, and the correlation between defaults was not symmetric. Assets collapse together far more violently than they rise together. The model assumed otherwise on all 3 counts. The T-copula addressed the tail problem directly by replacing the Gaussian with a heavier tail distribution controlled by a degrees of freedom parameter. Different mathematics, but the same insight the Gaussian copula was missing, that what happens to a system under stress is not what happens to that system at rest. The formula didn't fail Wall Street. Wall Street failed the formula, and that is not a story unique to 2008. Lee's 1999 paper on default correlation is in the description. So is Felix Salmon's 2009 Wired piece, which is probably the best account of how a 12-page paper became the engine of a global catastrophe. Whether that pattern is running somewhere right now is a question for another video.